Welcome, students. The electricity that powers the lights and appliances in your home arrives via power lines. The electricity travels through these power lines in a wave form, and in order for engineers to analyze the electrical currents, they must be well versed in the mathematics of complex numbers. Powers and roots of complex numbers are used to help describe the behavior of electricity as it moves from a power plant all the way to its destination, maybe a lamp lighting your room in your home. Let's get started answering the question, how does De Moivre's theorem relate to powers and roots of complex numbers? In order to answer the lesson question, you'll need to learn about powers and roots of complex numbers, prove De Moivre's theorem, determine powers of complex numbers, and establish roots of complex numbers. Here's some important words you'll learn in this lesson. Take a moment to type these important vocabulary words into your eNotes and check your glossary for their definitions. De Moivre's theorem, mathematical induction, powers of a complex number, and roots of unity. When two complex numbers are expressed in polar form, the multiplication rule can be used to determine their product. The multiplication rule is z1 times z2 is equal to r1 times r2 times the quantity cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. In order to determine the product, the moduli r get multiplied and the arguments theta get added. The result is a complex number that often has a modulus and argument that are unique from the first two numbers. This is reflected in the image on the right. The complex number z sub 3 represents the product of the numbers z sub 1 and z sub 2. This would be r1, r2, and r3. You can see that z sub 3 has a modulus, or distance from the origin, that is the product of the moduli r sub 1 and r sub 2. And the argument, or angle of rotation, for z sub 3 is the sum of the arguments theta 1 and theta 2.